Uh, Hello, this is us going to finish off section 4.1 part A. We're going to look at comparing two exponential functions and using Desmos to do any kind of comparison of two or more exponential functions, and then how you find the equation of an exponential function when you're just given a sketch with the location of one point on that exponential function. So here we are going. Suppose I wanted to compare 2 to the power of x and 6 to the power of x. What would the two look like? Well, they both have a base bigger than 1, so we know that their shape's going to be this kind of uphill thing. And what else could we get? Well, let's have a look. See what I can do here. So you should be looking at Desmos now. So I'll type in our first function, which is y equals 2 to the power of x. And yep, looks just like we thought it would. Now I'm going to type in y equals 6 to the power of x. And you can see that although it has that basic shape, you can see it flatlining on the left, passing through, there we go, y-intercept at 1, and then climbing upwards. But it's also quite clear that isn't 6 to the x gets bigger quicker. Let me change the scale a little bit. Maybe drop this down a touch. There we go. Maybe sketch it just a little bit more. There we go. Maybe I did too much. There we go. Now, I'm going to put in y equals 40 power of x. And you should not be surprised by what happens. Do you notice it's between 2 to the x and 6x? In fact, if I put in 3 to the power of x, oh no, 36x, 3 to the power of x, there we go. And what ones have I still to do? 5 to the power of x. Yeah. 2 to the power of x, 3 to the power of x, 4 to the power of x, 5 to the power of x, 6 to the power of x. They all have the same shape, right? They all look like the children's slide. They all have a horizontal asymptote on the left here of y equals 0. They all climb up to infinity as x gets larger, but they are a sequence, right? So just pretend for a minute that I didn't tell you which one of those was 2 to the power of x and which one of those was 5 to the power of x. But I told you that was the two functions. You can look at that graph and see immediately which one's which. Wouldn't this one, the black one, have to be 5 to the power of x because its base is bigger than 2 to the power of x? Because its base, 5, is bigger than 2, its y values get bigger quicker, right? Right? For smaller values of x, you get a bigger answer. You know, like 5 to the power of 3 is 125. 2 to the power of 3 is only 8. You can see them getting bigger. Okay, let's try comparing 2 to the power of x one half to the power of x. And for some bad reason, they're both red, so let's make this one blue. There. Pause and look at this for a minute. You see the red guy, 2 to the x? You see the blue guy, a half to the x? They've got the shapes you would expect. And they pass through the y-intercept of 1, as you'd expect. But do you notice that there's a lot of symmetry? In other words, look at them again. Is it the blue one and the red one just mirror images of each other? Isn't the y-axis of an axis of symmetry? And they are perfectly matched. You see that guy there? Height of 4? Same height? That guy happened at 2. This guy happened at -2. So there is an interesting property that if you take a base that's bigger and you take another one made of the reciprocal of the first one, so if the first one's 5 to the x, the second one's a fifth to the x, then those two functions are exactly mirror images of each other. And you can have fun in Desmos playing about with those and seeing what comes up. So the last thing we're going to look at, can you find the formula of an exponential function if all you're given is that function, right? And the answer is yes. So imagine that I gave you an exponential function. All I told you is that it was a to the power of x. And you need to just find out what a is to get the function. Well, there's no point in looking at that guy because that guy's 1 for everybody. So let's give you a point here and tell you that that coordinates is 4, 16. So how do we solve? How do you find the base A using that? Well, technically 4 is the x and 16 is the y. So if I think of this as not f of x, but y equals a of x, which is totally equivalent, I can put 16 in here, and I can do a to the power of 4 here. And then I just need to figure out what number would a need to be, right, to get 16. Well, as long as you do it to both sides, it's okay, though. So what about finding the 4th root of 16, right? Or if you prefer, 16 to the power of a quarter. And if you do that on your calculator, you get 2. Suppose I give you another one. Suppose I have a function that's curving downward. I can help. And let's suppose I tell you that this guy here has coordinates 3, comma, let's see, what fraction will I do? Okay. Then we know it's going to be a to the power of x. So we'll call it y equals a to the power of x. The x is 3, and the y is, 81. So to get a, I take the cube root of 1 over 81. And you could certainly do that on your calculator. And if you did, hopefully you'll get, let's just check this out. 3. Oops. Can you pretend that that was 27? Because I made an oopsie. And what do you get? Well, cube root of 127. Right? So what would you start with? I'm going to my calculator and I'll show you. Hopefully it'll come out the way I want it to. So I need to share the screen. There we go. So I've got a bracket, 1 divided by 27, close the brackets. Now you get a cube root. I know there is a cube root button hidden somewhere, but I'm just going to go to the power of a third, which is the same thing. A square root, for instance, would be a half. Get that guy. And then math, option 1, which means take your answer and make it a fraction. And there you go. We got the answer. A is the third. And now we can tell everyone that this function here is 1/3. The base is a to x. Oh, and this one here that was 2, you can say that the function is 2 to the power of x. So that would be your answer to this curve. There is your answer to that one. And that is us.